Welcome to Jeremy's IT Lab. This is a free complete course for the CCNA. If you like these videos, please subscribe to follow along with the series. Also, please like and leave a comment, and share the video to help spread this free series of videos. Thanks for your help. In this video, we will cover IPv6. As you already know, up to this point in the course, we have been covering only IPv4. But IPv6 is the future, and it is starting to take over networks all over the world. IPv6 brings multiple improvements over IPv4, but there is one main reason for the switch to IPv6. IPv6 is covered in a few areas of the official exam topics list. Topic 1.8 says you must be able to configure and verify IPv6 addressing and prefixes, and 1.9 says you must be able to compare various IPv6 address types. You should also be able to configure and verify the same kinds of static routes in IPv6 that we already covered in IPv4. I considered trying to fit all of this into a single video, but have decided to split it up. A lot of CCNA candidates don't feel confident about their IPv6 knowledge. I think that's because we spend so much time learning IPv4, but then so many courses just briefly cover IPv6 and then never mention it again. Let's take our time to cover IPv6 and make sure you feel confident about answering IPv6 questions on the exam. Here's what we'll cover in this video. First, let's review hexadecimal. I told you about hexadecimal when we covered MAC addresses, but let's make sure you really understand hexadecimal because IPv6 addresses are written in hexadecimal too. Then I'll give an overview of why IPv6 is necessary, why we are starting to move away from IPv4. I'll give you a basic overview of IPv6, specifically IPv6 addresses. Finally, I'll show you how to configure IPv6 addresses on Cisco devices. Watch until the end of the video for a bonus practice question from Boson ExSim, the best practice exams for the CCNA. I use them to study for my exams, and they are the best practice exams out there. If you want to get Boson ExSim, follow the link in the video description. Before talking about IPv6, you may be wondering, what about IPv5? I think I mentioned this earlier in the course, but here's another quick review. Internet Stream Protocol was developed in the late 1970s, although it was never actually introduced for public use. It was never called IPv5, but it used a value of 5 in the version field of the IP header. If you remember, day 10 of this course covered the IPv4 header, and the very first field is the version field. IPv4 uses a value of 4, and Internet Stream Protocol used a value of 5. So, to avoid confusion, when the successor to IPv4 was being developed, it was named IPv6, and it uses a value of 6 in the version field of the header. Now let's review hexadecimal. The three numbering systems you should know for the CCNA are binary, also called base 2. 0b can be used as a prefix before a binary number, so you know that the number is binary. For example, look at this number, a 1 and a 0. Is that decimal 10? Or binary 10, which is equal to decimal 2? Or is it perhaps hexadecimal 10, which is equivalent to decimal 16? We can't know. By using the prefix 0b, we can make it clear that this is a binary number. Now, why is base 2 another name for binary? It's because there are only two available digits in binary, 0 and 1. All numbers are represented using just these two digits. But you're already familiar with binary. The next numbering system is decimal, or base 10. You can use the prefix 0d to indicate decimal. As the name base 10 suggests, there are 10 available digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Finally, there is hexadecimal, also known as base 16. You can use the prefix 0x to indicate hexadecimal, as I have mentioned a couple times already in the course. These are the 16 digits available in hexadecimal. 0 to 9 are the same as decimal, and then A, B, C, D, E, and F are used as well. Here's a chart comparing the three, from 0 up to decimal 15. First, notice that up to 9, decimal and hexadecimal are the same. However, the decimal system then runs out of digits, so it has to add a second column, and 10 is written as 10. Hexadecimal expresses the same value with a single digit, A. 11 is B, 12 is C, 13 is D, 14 is E, and 15 is F. Okay, now let me point out a few other things. Notice that these binary numbers have leading zeros at the front. For example, decimal 3 is written as 0011 instead of just 11. You don't actually have to do this in binary. You can just write it as 11. So why did I write all of these numbers as 4 digits, even though the leading zeros are unnecessary? It's because I want to emphasize that each hexadecimal digit contains 4 bits of information. For example, the maximum value of 4 binary bits, 1111, gives us the maximum hexadecimal digit, F. This is very important for converting between binary and hexadecimal, and decimal and hexadecimal. From this chart, I recommend memorizing the decimal to hexadecimal conversions. It's not difficult. Just remember that 10 is A, 11 is B, 12 is C, 13 is D, 14 is E, and 15 is F. Also, be able to convert between binary and decimal. You already know that. It shouldn't be a problem. If it is a problem, go back and watch the IPv4 addressing and subnetting videos for review. If you can do those two things, convert between decimal and hexadecimal up to 15, and convert between decimal and binary, you'll have no problem converting either decimal or binary to hexadecimal. Let's walk through some conversions. Binary 1101, 1011 is equal to what in hexadecimal? So this is 8 binary bits. Remember, each hexadecimal digit contains 4 bits of information. So split the number into 4-bit groups, 1101 and 1011. Then convert each of those 4-bit groups to decimal. 1101 is 8 plus 4 plus 1, so 13. 1011 is 8 plus 2 plus 1, so 11. Then convert those decimal numbers to hexadecimal. You should have these conversions memorized. 13 is D, and 11 is B. Simply put those two hexadecimal digits together, and you have the answer. Binary 1101, 1011 is equal to hexadecimal DB. To check, you can use a calculator. For example, from the Windows 10 calculator app, click the top left menu button. Then select the Programmer Calculator. In the Programmer Calculator, you can select between hexadecimal, decimal, octal, which is base 8, and binary. I selected hexadecimal and typed in DB. As you can see, it is equal to binary 1101, 1011. If you don't use Windows 10, your calculator app probably has a similar option to the programmer mode. Or you can just do a Google search for a binary, decimal, and hexadecimal converter. In the real world, you'd use a calculator to do any conversions between binary, decimal, and hexadecimal. However, it's important to be able to do the conversions yourself to make sure you actually understand the concepts. Let's do a few more practice questions for binary to hexadecimal. Pause the video to try this one out yourself. Do the steps as written. Let's check. First, split the number into 4-bit groups. Convert each group to decimal. Convert each decimal number to hexadecimal. And there's the answer. Binary 0010, 1111 is equal to hexadecimal 2F. We'll do one more for binary to hex. Pause the video to try it out. Let's check. First, split the number into 4-bit groups. Convert each group to decimal. Convert each decimal number to hexadecimal. And there's the answer. Binary 10000001 is equal to hexadecimal 81. How about converting from hexadecimal to binary? Basically, it's just the reverse process. Convert to decimal, then to binary. For example, what's hexadecimal EC in binary? First, split up the hexadecimal digits. Then convert them to decimal. E is 14 and C is 12. Then convert each decimal number to binary. And that's the answer. Hexadecimal EC is equal to binary 1110, 1100. Okay, here's another one. Pause the video to try it out yourself. convert hexadecimal 2b to binary. Let's check. First, split up the hexadecimal digits. Then convert them to decimal. 2 is 2, and b is 11. Then convert each decimal number to binary. And that's the answer. Hexadecimal 2b is equal to binary 00101011. Okay, last one. Pause the video to try it out yourself. Convert hexadecimal D7 to binary. Let's check. First, split up the hexadecimal digits. Then convert them to decimal. D is 13 and 7 is 7. Then convert each decimal number to binary. And that's the answer. Hexadecimal D7 is equal to binary 11010111. Okay, that's all for the conversion practice. It's not the main focus of this video. If you don't feel comfortable converting between them yet, do some more practice. Write out a random 8-bit, 1-byte number and convert it to hexadecimal. Do the opposite too. Also try it with numbers that aren't 8 bits. See if you can figure it out. Now let's move on to the next topic. And the next topic is this. Why IPv6? The main reason is that there simply aren't enough IPv4 addresses available. How many IPv4 addresses are there? An IPv4 address is 32 bits long, so that means there are 4,294,967,296 IPv4 addresses available. That may seem like a lot, but in our modern world, where the internet is everywhere, it's simply not enough. When IPv4 was being designed 30 years ago, the creators had no idea the internet would be as large as it is today. They thought 32 bits would provide more than enough addresses. However, we have known about the IPv4 address exhaustion problem for a long time, and several techniques have been used to preserve the space. VLSM, variable length subnet masks, is one of the techniques that allows IPv4 address space to be preserved. Private IPv4 addresses and NAT, network address translation, are two others that have made a huge difference as well. Both of those will be covered soon in the course. Those techniques have been very useful in preserving the IPv4 address space. However, they are just short-term solutions. The long-term solution is to transition to IPv6. Let me briefly explain how IPv4 addresses are assigned. IPv4 address assignments are controlled by IANA, the Internet Assigned Numbers Authority. I mentioned IANA in the last video about TCP and UDP also. IANA distributes IPv4 address space to various RIRs, regional internet registries, which then assign them to companies that need them. For example, an internet service provider would ask its local RIR to assign it IP addresses which can then be used by its customers. This is a map showing the various RIRs. To be honest, I don't know the proper pronunciation of each of the names, but Afrinic controls Africa, APNIC controls Asia Pacific, ARIN controls Canada, many Caribbean and North Atlantic islands and the US, LACNIC controls Latin America and the Caribbean, and RIPE NCC controls Europe, the Middle East, and parts of Central Asia. However, these RIRs are almost all out of IPv4 addresses. For example, in September 2015, ARIN declared exhaustion of the ARIN IPv4 address pool. They don't have any more addresses to assign, unless a company goes out of business and ARIN can reclaim their addresses, for example. Here's another one. In August 2020, LACNIC announced that it had made its final IPv4 allocation. The other RIRs have similar problems too. So, as you can see, the situation is pretty serious. There just aren't enough IPv4 addresses for our modern world. We need something capable of supporting our interconnected world now and far into the future. That is IPv6. Let's finally get into the specifics. There is actually a lot of interesting history about IPv4 address exhaustion and IPv6, but that's enough for this video. I think you can see why we need to transition to IPv6. If you want to read a little about it, search for IPv4 address exhaustion on Wikipedia. So let's talk about IPv6. An IPv6 address is 128 bits. That's 4 times the number of bits in an IPv4 address, which is 32 bits. At first, you might think that 4 times the number of bits means that there are 4 times the number of addresses. That's wrong. Every additional bit doubles the number of possible addresses. 32 bits allows for about 4 billion addresses. 33 bits would allow about 8 billion, 34 bits would allow about 16 billion, etc. So, how many IPv6 addresses are there? There are 340 undecillion, 282 decillion, 366 noncillion, 920 octillion, 938 septillion, 463 sextillion, 463 quintillion, 374 quadrillion, 607 trillion, 431 billion, 768 million, 211,000, and 456 IPv6 addresses. Yes, I had to search on Google to learn how to say that number. But no, you don't have to memorize it. For comparison, here's the number of IPv4 addresses again. Here's an example of an IPv6 address in binary. That's a lot of ones and zeros. If you write that in dotted decimal like an IPv4 address, it looks like this. However, as I've already said, IPv6 addresses aren't written in dotted decimal. They are written in hexadecimal. Here's that same address written in hexadecimal. An IPv6 address is 128 bits, and as I said, each hexadecimal digit contains 4 bits of information. 128 bits divided by 4 is 32. So an IPv6 address is written as 32 hexadecimal characters, divided into 8 groups of 4 using colons. This is still longer and more difficult to read and remember than an IPv4 address, but that's unavoidable. There is 4 times the amount of information in this address compared to an IPv4 address. But there's some good news. IPv6 addresses use the slash notation to indicate the prefix length, even when configuring the address in the Cisco iOS CLI. No more dotted decimal subnet masks. This /64, for example, means the first half of the address would be the network portion, and the second half would be the host portion. In addition, there are a couple methods to shorten IPv6 addresses to make them simpler. Let's look at those methods to shorten IPv6 addresses. First up, leading zeros can be removed. Look at this IPv6 address. Leading zeros are any zeros at the beginning of any of the quartets of 4 hexadecimal digits. These are the leading zeros in this address. So we can simply remove them. Now the address can be written like this. The zeros are still part of the address, but there's no need to write them, and it looks simpler like this. Okay, there's one more technique to shorten an IPv6 address. Consecutive quartets of all zeros can be replaced with a double colon. For example, in the address below, there are 4 consecutive quartets of all zeros. You can shorten the address like this, replacing those quartets with a double colon. Why are you able to do this? It's because we know an IPv6 address is 8 quartets in length. We can only see 4 quartets now, so we know the double colon means that there are 4 quartets of all zeros. But let's not stop there. You can combine both methods, removing leading zeros and using the double colon. Now this address looks much easier to handle. But there's a limitation here. Consecutive quartets of zeros can only be abbreviated once in an IPv6 address. Why is that? Well, look at this address here. You might try to shorten it like this. But now we have a problem. We know there should be 8 quartets in total, so there are 5 quartets of all zeros. But how many quartets of zeros are here? 2? 3? We can't know. How about here? Maybe there are 2 quartets on the left and 3 on the right, or maybe 3 on the left and 2 on the right. So this is why we can only abbreviate the all zero quartets once in an address. Instead, we should shorten the address like this. The left side has 3 all zero quartets, so I replace them with a double colon. On the right side, which has 2 all zero quartets, I simply removed the leading zeros. Here's a few questions to practice shortening IPv6 addresses. Pause the video and try to complete each. Okay, here are the answers. Here's the first one. You're able to remove the leading zeros and use the double colon. Next one. Note that there are 2 sets of consecutive zeros, but you can only use the double colon to replace one set. Okay, next one. Like the previous 2, you're able to remove the leading zeros and use the double colon. Next one. There are some leading zeros you can remove in this one, but not consecutive quartets of all zeros. Okay, last one. You're able to replace 5 quartets of zeros with the double colon. You should also be able to take a shortened IPv6 address and expand it into a full IPv6 address. Here's an example of how to do that. First, put leading zeros where needed. Remember that all quartets should have 4 hexadecimal characters. That's why they're called quartets. Where can we put leading zeros in this example shortened address? These 3 quartets here. So now the address looks like this, but we're not finished. If a double colon is used, we should replace it with all 0 quartets, and make sure there are 8 quartets in total. There is a double colon here, so we can expand the address further. How many quartets are there? There are 5. Actually, there are 8, but currently only 5 are written. To make 8 total quartets, simply add 3 quartets of zeros. Here are a few practice questions for expanding shortened IPv6 addresses. Pause the video to solve them. Okay, here are the answers. First one, second one, third one, fourth one, and the fifth one. I will talk about different IPv6 address types in another video, but each of these addresses is a different type of address. IPv4 has different kinds of addresses like multicast addresses, loopback addresses, etc., and so does IPv6. But as I said, that's a topic for another video. Next up, let's see how to find the IPv6 prefix, the network address, from a particular host address. We've already done this before for IPv4. Change all of the host bits to 0, and then you have the prefix, the network address. But let's try it out for IPv6. Typically, an enterprise requesting IPv6 addresses from their ISP will receive a /48 block. Also, typically IPv6 subnets use a /64 prefix length. So the enterprise received a /48 block, but the usual prefix length is /64. This means that an enterprise has 16 bits to use to make subnets, and the remaining 64 bits can be used for hosts. I think an example will make this clearer. Here's an IPv6 address. This part in blue is the /48 block assigned by the ISP. It's called the global routing prefix. Note that this example is for the IPv6 global unicast address type. As I said before, there are multiple IPv6 address types, which I will cover in another video. But these global unicast addresses are the regular IPv6 addresses that hosts can use over the internet. They aren't private addresses, or multicast addresses, etc. Okay, the next 16 bits, 4 hex digits, are called the subnet identifier. Because the enterprise received a /48 block from the ISP, but IPv6 addresses usually use a /64 prefix length, these 16 bits are free to use to make different subnets. Together, these two parts make the network portion of the address, the IPv6 network prefix. Then the last 64 bits are the host bits. That is a huge amount of hosts per subnet. You'll never need that many. But the convention is to use a /64 prefix length. However, that doesn't mean you'll only ever see /64 prefix lengths. So, we'll practice using IPv6 addresses with various prefix lengths. Finding the prefix of an IPv6 address with a /64 prefix length is easy. Simply make the second half of the address all zeros. That's what I did here, and notice I shortened the address by removing a leading 0 and replaced the host portion, which is all zeros, with a double colon. Even if the prefix length isn't /64, if the prefix length is a multiple of 4, it's easy to find the prefix length. Why is that? It's because each hexadecimal character is 4 bits. 56 is a multiple of 4, so let me show you how to find the prefix of this IPv6 address. This first quartet is the first 16 bits of the address. This one brings it to 32 bits, 48 bits. This 2 contains the next 4 bits, so 52. And this 1 contains another 4 bits, so 56 bits. So these first 14 characters are the network portion of the address, the prefix. Everything after is the host portion, so we can change them all to 0 to find the prefix. Here it is, after removing leading zeros and using the double colon. Let me point out that you can't remove these zeros. Even though they are part of the host portion of the address, they are not leading zeros, so you can't remove them. For example, if you were to shorten the address like this, removing those two zeros, if you add those leading zeros back, the prefix would be this, which is a totally different network address than the original one. So remember that point. You can only remove the leading zeros. So that's all quite simple. Find where the network portion ends and change all digits after it to 0. But with an IPv6 address like this, you need to go through a couple more steps. The prefix length is /93, which isn't a multiple of 4. So that means that the network portion ends in the middle of one of the hexadecimal digits. Let's find which one. 16 bits, 32 bits, 48 bits, 64 bits, 80 bits, 84, 88, and this 7 brings us up to 92 bits. So the network portion includes all of these characters, plus the first bit of this B. So in order to properly write out the network prefix, we need to look into the binary. As you know, hexadecimal B is equal to decimal 11. Decimal 11 is written as 1011 in binary. Only this first bit is part of the network portion of the address. So let's change all of the other bits to 0. Now we have binary 1000. Change that back to decimal, which is 8. It's also written as 8 in hexadecimal. So when we write out the network prefix, we have to change the B to an 8, because we changed the host bits all to 0. So here's the network prefix. Notice the 8 instead of the B. I hope you can see the importance of really understanding binary. If you don't know binary, it would be tough for you to know that the B becomes an 8 when all of the host bits are changed to 0. The same goes for IPv4. If you don't know binary, you can't really understand IPv4 addressing and subnetting. Here are some practice questions. Find the prefix of each of these IPv6 addresses. Pause the video now to do that. Okay, here are the answers. First one, second one, third one, fourth one, and fifth one. Note that you don't have to write out the shortened version. You can write out the whole address if you prefer. If you still want some more practice, try writing out some random IPv6 addresses with random prefix lengths yourself, and then try to find the prefix of each address. So we've only covered the absolute basics of IPv6, specifically IPv6 addresses. But I want to include a lab with each lecture video as often as possible. So let's cover some very basic IPv6 configuration. I'll just show you how to configure IPv6 addresses on router interfaces. And then in the next video, you can try it out in Packet Tracer. So R1 has 3 interfaces, each connected to a different subnet. 2001 DB800/64 on the G00 interface, 01/64 on G01, and 02/64 on G02. In this example, the company was assigned a /48 address block and is using the last quartet of the prefix to make different subnets. Just a side point. You may be wondering why I've been using the 2001 DB8 range a lot. That's because this range of IPv6 addresses has been reserved for examples and documentation. They should never actually be used in real networks, but you're free to use them in examples like this. So here's the configuration. First up, you have to use the command IPv6 unicast routing. This command allows the routers to perform IPv6 routing. If you don't enable this, it's not going to actually forward IPv6 packets. Next up, I configured the G00 interface. The command to configure an IPv6 address is IPv6 address, followed by the address and prefix length. You'll notice that a lot of IPv6 commands are the same as in IPv4, except instead of IP, the command uses IPv6. Also notice that you can use the shortened version of the IPv6 address. The router will understand. Remember to use no shutdown to enable the interface too. I did the same thing on G01 and then G02, except this time I typed out the entire address. You can use the whole address, the shortened address, or even a partially shortened address. The router will understand what you mean. Now let's confirm the configurations. I use the command show IPv6 interface brief. Again, same as the IPv4 command, you just have to use IPv6. There are a few things to point out here. First up, notice that the shortened version of the address is displayed, not all 32 hex digits. Actually, the address on the G00 interface is shortened even more than the shortened address I typed. To emphasize that the first 4 quartets are the network portion, I typed out these 2 zeros here in the network diagram and when I entered the command. But they can be included in the double colon also, if you want to shorten the address as much as possible. Okay, next thing to point out, something you probably already noticed. Each of these interfaces has 2 IPv6 addresses, even though we only configured 1. These are called link local addresses, and they are automatically configured on an interface when you configure an IPv6 address, when IPv6 is enabled on the interface. I will cover these in day 32, when I cover the various IPv6 address types. But if you want to read about them before that, Wikipedia has a good article about them. IPv4 has link local addresses as well, although they aren't automatically enabled on IPv4 interfaces. Anyway, as I said, I'll cover those in day 32. Before moving on to the quiz, let's review what we covered in today's video. First up, we reviewed hexadecimal and practiced converting between it and binary. Although we briefly covered hexadecimal when learning about MAC addresses, for IPv6 it's even more important to be comfortable with it. Then I introduced why IPv6 is necessary. Basically, there aren't enough IPv4 addresses for our modern world. I covered the basics of IPv6, and the main focus of today's video was on IPv6 addresses, which are 128 bits in length and usually written using hexadecimal. Finally, I showed you the basic commands to enable IPv6 on a router, and then configure IPv6 addresses on an interface. There is still a lot more that we have to cover about IPv6, but I hope this video was a good start. Make sure to watch until the end of the quiz for a bonus question from Boson ExSim, the best practice exams for the CCNA. They're the practice exams I use to prepare for the CCNA and CCNP exams, and they really are the best. If you want to get ExSim, follow the link in the video description. Okay, let's move on to question 1 of the quiz. Which of the following are valid IPv6 addresses? Select 3. Here are the options. Pause the video now to find the answers. Only 3 of them are valid IPv6 addresses. Okay, let's check the answers. The valid IPv6 addresses are A, B, and E. Why is C invalid? It has a G in the 4th quartet. IPv6 addresses use hexadecimal, which only includes 0 to 9, and A, B, C, D, E, and F. Why is D invalid? It has 9 quartets. An IPv6 address should have only 8 quartets of 4 hexadecimal digits each, separated by colons. And how about F? It's using the double colon twice. Remember, you can only use the double colon to shorten an IPv6 address once. Okay, let's go to question 2. Which of the following is a correctly abbreviated version of the IPv6 address below? Here are the 4 options. Pause the video now to select the correct one. The correct answer is D. All of these abbreviations involve removing zeros, but remember that you can only remove leading zeros from an IPv6 address to shorten it, the zeros at the beginning of the quartet. So only D is a correct abbreviation of the address. Let's go to question 3. Which of the following commands must be used to enable a router to perform IPv6 routing? A. IPv6 unicast routing from interface config mode. B. IPv6 unicast routing from global config mode. C. IPv6 routing from global config mode. Or D. IPv6 routing from interface config mode. Pause the video to think about your answer. The answer is B. IPv6 unicast routing, entered in global config mode, must be used to enable the router to perform IPv6 routing. Okay, we had lots of practice questions earlier in the video, so let's finish the quiz here. Now let's do a bonus question from Boson ExSim for CCNA. Okay, here's today's Boson ExSim practice question. This question actually covers something we didn't cover in the video, but I think you can answer it. So here's the question. What command would you issue on router A so that traffic can be routed to router C. Select the best answer. So this is a question about static routing using IPv6. However, the IPv6 static route command is exactly the same as in IPv4. Like I said in the video, a lot of IPv6 commands are like that. The only difference is, instead of IP route, it's IPv6 route. So the command is IPv6 route, followed by the destination. You can see the network address and the prefix length here, and then the next hop. Okay, so that's the IPv6 static route command. So knowing that, you should be able to answer this question. So pause the video here and try to find the correct answer. Okay, hopefully you found the answer. So let's check it out. So router A needs to reach router C, which is in the 2001 DB82/64 network. So that should be the destination in the static route command. So that means the correct answer is either B or D, because A and C have the destination 2001 DB81/64, which is not correct. So is the correct answer B or D? Let's see. So the next hop should be router B's interface in the 2001 DB81 network. So that is 2. So which one has the correct next hop? This one here, B, 2001 DB81, 2. That looks correct. How about D? The next hop is 2001 DB822. That is not correct. That would mean router C is the next hop, but router A doesn't even know how to reach router C yet. Okay, so B should be the correct answer. I will click on Show Answer, and indeed that is correct. So here is Boson's explanation. You can pause the video here to read that. Also notice there is some Cisco documentation included. This is available free online, and it's a great study resource. And also it shows you which category of the exam topics this question is from, and it is from IP connectivity. Okay, so that is an example question from Boson ExSim for CCNA. If you're looking for CCNA practice exams, Boson ExSim is really the best you can get. These are fantastic practice exams. I use them when preparing for my CCNA and CCNP, so I highly recommend them. If you want to get a copy of Boson ExSim, follow the link in the video description. There are supplementary materials for this video. There is a flashcard deck to use with the software Anki. There will also be a packet tracer practice lab, so you can get some hands-on practice. That will be in the next video. Sign up for my mailing list via the link in the description, and I'll send you all of the flashcards and packet tracer lab files for the course. Before finishing today's video, I want to thank my JCNP level channel members. To join, please click the Join button under the video. Thank you to Magrathia, Unjabulo, Benjamin, Deepak, Tsepiso, Justin, Loki, The Gun Guy, Neil, Prakash, Nasir, Erlason, Apaji, Wasim, Marco, Florian, Daming, Koni, Joshua, Gilmar, Samil, Ed, Value, John, Funnydart, Scott, Hassan, Gerard, Joyce, Marek, Velvajakum, C-Mode, Johan, Mark, Yusuf, CD, Boson Software, Charlesetta, Devin, Lito, Jonathan, and Vance. Sorry if I pronounced your name incorrectly, but thank you so much for your support. One of you is still displaying as channel failed to load. If this is you, please let me know and I'll see if YouTube can fix it. This is the list of JCNP level members at the time of recording, by the way. October 8th, 2020. If you signed up recently and your name isn't on here, don't worry. You'll be in future videos. Thank you for watching. Please subscribe to the channel, like the video, leave a comment, and share the video with anyone else studying for the CCNA. If you want to leave a tip, check the links in the description. I'm also a Brave verified publisher and accept BAT or Basic Attention Token tips via the Brave browser. That's all for now.